Okay, so welcome to my physical chemistry talks. Right now, I'm attempting to back up some of my earlier talks that I did not get a chance to do due to the whole COVID-19 starting in mid-semester. So here's a bunch of general chemistry. Well, here's the start of my physical chemistry, starting with chapter 1. And here's how the class will go. Essentially, I'm warning you that one, you need to know at least up to integral calculus to do this, because we'll do integrals, we'll do derivatives, we'll do partial derivatives and partial differentiation. So you at least need to know those terminology and how to use that, or else you won't really be able to get very far. You need to have an analytical and inquiring mind. We need to understand the proofs to derive these equations, be able to think about how do we attack this question and get it. So, and yeah, you need at least a reasonable amount of math. If you haven't at least had calculus, you're gonna struggle. So you need to know about canceling units, cross multiply, and all that stuff that hopefully you have by now. But if you don't, it's gonna be rough. Now, it's hard, but you get through this and you'll be a better student, all things considered. So think about thermodynamics. So what are we doing? We're going to take, when we think of chemistry for the most part, we think of microscopic atoms and molecules and think about like, whoa, what's going on here? Now we're going to use this and scale this up to macroscopic variables such as pressure, volume, and temperature, get to a macroscopic scale where we're talking about energy that we can actually use. This is really a lot of applied chemistry that goes into engineering and physics and all those tough math courses that we need. So we're going to calculate the effects of changing pressure and temperature on equilibrium. That previously we just looked at changing concentrations. Like we can calculate the energy efficiency of a combustion engine and fuel cells. We can calculate and understand the thermodynamics of batteries. We can determine kinetics in real life situations, not just a pretty lame one-step reaction. So how I'm going to start off with this really rather intense proof, really, that we all know that the ideal gas equation is PV equals nRT. But how did we get that? It relates physics of individual molecules to the macroscopic nature of gases. So how did we get this? So first thing we're going to talk about is remember that we have a bottle of gas. We can describe that gas with a pressure, a volume, and a temperature. And gas molecules will have a velocity such that the velocity squared is equal to the velocity of each individual terms in the x, y, and z dimension, because gases are traveling in x, y, and z. We're going to focus mainly on the x direction, because when all directions are the same, it's easier just to focus on, all directions are equally important. We're going to just focus on one to try to simplify this down. So the first thing we need to know is that kinetic energy of the translational motion, or sigma TR, is equal to 1/2 times mass times velocity squared. And since we're defining this translational motion in the x direction, it's v of the x squared. Now, we need to remember that energy is conserved through elastic collisions against a barrier. And these collisions will generate the pressure. Why is this going to generate pressure? Because pressure is specifically defined as force over area. So we're going to use some math and some terms to get this in one direction. So the first thing we're going to get is turn pressure into the change in density, the change in momentum over area, the change in time. I'm going to switch to so first part of this proof. So let's start with just this. The pressure is equal to force over area. That's our physics description of what pressure is. But force can also be described as mass times acceleration. And so that mass times acceleration over area. And acceleration is defined as the change in velocity with respect to time. So mass over area, factoring that out, change in velocity over change in time. dv dt. Now, density is defined as mass times velocity. So factoring that mv, dmv for dt, we get our, this is where we get our delta p, which is our change in momentum over area times the change in time. So that's our first part of this proof. So we can get pressure is the changing momentum of a gas molecule described over a surface area that's colliding with time over change in time. Share screen and back to. So, okay, that in mind. Now, because of this, we're looking at the point of collision. What is the change in momentum of a gas molecule? So a gas molecule is moving left to right, hits a wall, and goes right to left. The momentum is positive mv, and if this is elastic collision where momentum is conserved, it becomes negative mv. And so the net difference is negative 2 mass times the velocity for the momentum for that. And of course, for the wall, it's positive 2 mass times velocity. Now, that is just looking at one particle here. We have thousands of molecules of gas or particles of gas. So we need to scale this up. So what is the total momentum that this wall is feeling? The total momentum is going to be the sum of all the momentums of each molecule times the total number of molecules. Now, of course, this is the momentum over the whole time, but we want to define this as a specific time. How long? So how many molecules will strike within a given time? So back to our little proofing board. So okay, so clear this. So we're going to try to find our number of collisions over time. So number collisions over time. Now, for that, we need idea of velocity, the volume of that box. So a volume is defined as the area of the wall times the shape, the essentially length of the box. Now this is, we're talking about the change in x. So to go from one side of that box to the other side, the area is of course y times z, xyz of that box. Now, since well, it's going to be more convenient to leave this as area. So now why this is important, why do we say change in x? As the particle is moving across that box, we can say, well, the change in x of a moving gas particle is equal to velocity of that gas particle times a change in time. So you know the distance traveled by a set velocity and a change in time for a particle to get from one wall to the other wall. So there's our volume. Now we're going to look at the number of collisions. We're going to say number n. Now, as we get a little weird, we use this term and we're only going to really use it here, but n tilde is our number density. Number density. So kind of how many relates to how many gas particles are in this box. And we're going to say the number of collisions then is times, as I said, our A Vx delta t. But it's also times 1/2, because at any given time, the gas particles could be, half of them are moving in one direction and half are moving on the other, on average. Now, replacing n tilde with something you might more readily see, n tilde can be abbreviated for the moles times Avogadro's number divided by the volume. So a density. So number density, this is telling me how many atoms per a set volume. And times, once again, the number of collisions, A Vx delta t times 1/2. So just looking real quick. So that right there is the second part of there. So that's talking about the number of collisions. That's how we can label the number of collisions. But now we're going to combine these two terms together. So if we say that the total momentum felt in the box is the momentum of a molecule times times the number of molecules, and the momentum is equal to, we said, 2 mass times the velocity. So we say that the total number of the P total is equal to this is for one molecule, 2 mvx at times the number of collisions. Well, something nice happens. 2 mvx, use our term that we just got, n, small n, Avogadro's number over V, times A Vx delta t over 2. So we start getting some things canceling out. We got n na a over V delta T times mass times the average distribution of velocity squared. Now here's where we're going to bring it all home. Remember our pressure. Pressure is force over area, and force is momentum over time. So force thus becomes this term divided by delta T. So delta T and that cancel out. So we cancel that out. Now, once again, then pressure becomes force divided by area. Pressure is force over area, so it becomes this whole thing divided by area. Area cancels out. So now, let's move this up. We have pressure equals N. N A, Avogadro's number, over V times mass dx squared. Now, finally, we get back to that whole translational kinetic energy. We said that kinetic energy, what is it, the sigma E of kinetic was equal to 1/2 mv squared. Well, another convenient number is we can look at translational kinetic energy as also being equal to Boltzmann's constant, K sub B, times the temperature of a molecule divided by 2. So with that in mind, mvx squared can be exchanged for K sub B times T. So we have right here P equals N T over V times Avogadro's number times Boltzmann's constant. Now, if you multiply those two numbers together, you'll get the units for R in joules per mole, 8.314 joules per mole. So we get P equals N R T. P equals N R T over V. And that is an example of R proofing in action. That essentially here, we've just used a little bit of physics, well, a lot of physics to be honest, and some logic, and gone through and how did we get these numbers? How did we get the magic constant R? It's coming from real constants that we already know. So now the first chapter is pretty basic. We're going to start by looking at temperature and ideal gases and all that jazz. So first thing we need to talk about is temperature and thermal equilibrium. What is temperature? Temperature is actually a really abstract quantity that we can only really measure indirectly by looking at the volume of mercury in a narrow capillary tube. We can look at it as electromotive force, which is our voltage that can be generated at a junction of two different metals. We can look at it as electrical resistance over a platinum wire. We can say, oh, it feels cold or it feels hot, but we don't really have a real good idea of what temperature really is. I mean, microscopically, as we just saw, we can correlate temperature to kinetic energy, but it's really vague when it comes to big things like hot and cold. So for the sake of a more concrete number, we'll think temperature is in terms of the ideal gas equation. So we can say temperature is the pressure of a gas with a set volume mole density at a constant R. So we can relate essentially with a set density, what is the pressure of the gas, and relate that to the temperature. So a lot of these systems we'll look at, we can maybe define them at thermal equilibrium. What will that mean? If I put two systems with the same ratio of gas particles and they are at the same pressure, they must thus also be at the same temperature. If I bring them into direct contact, we would see no heat transfer. Now, when we look at temperature as a scale, thermometer will measure a fixed temperature as a function of volume. We can use a electrical thermometer to measure as a voltage or resistance, but we can measure it as essentially T at a constant X is equal to a constant A plus a constant variable B times X. A and B are fixed for that thermometer. Our earliest thermometers were mercury in a glass tube. Our mercury's volume depends linearly on the temperature over the entire liquid state of mercury, which is from negative 38.8 degrees Celsius to 356.7 degrees Celsius. So it's really linear so that we can make marks on the tube for that set volume and know where that temperature is at. The volume of was standardized as arbitrary 0 to 100 in Celsius, just to give us 100 equal divisions for centigrade scale, which is centigrade is slightly different from Celsius. But a gas thermometer can work under a similar principle in that we measure the pressure of a fixed volume of gas within a temperature range. But using this idea, this gas thermometer, the data could be extrapolated to a hypothetical pressure 0 at certain volumes of gas. And this graph down here shows if I took different concentrations of gas and run them through the pressure temperature scale, they all extrapolate to the same 0 point, which is our negative 273 degrees Celsius, which gave us our absolute 0 in our Kelvin scale. Now, there's some crucial terminology for our thermodynamics before we go any further. We're going to be using these all throughout this class, so you should learn them. When we talk about a system, a thermodynamic system is the region in which all relevant chemistry occurs, the region in which we care about all the variables. It's our region where the process under study is happening. Now we can define this as narrowly or as widely as we need to solve this. Could be the chemical reaction, it could be a gas expanding, contracting, could be a solution where a reaction is occurring, could be a whole box. It all depends what we need. The surroundings, on the other hand, is going to be everything outside of that box. You expand the surroundings to be complete, we would have the rest of the universe. And so if we add the system and surroundings, we have the entire thing. Now, a boundary is specifically any interface between the system and surroundings. Now, most times we'll be talking about a wall, but this could be just the space between a solid and a liquid, or a liquid and a gas, like the air above a beaker. What is the boundary between those two? Now, a wall is just specifically a solid boundary between the system and surroundings. So, not the air above it. So we have three types of systems we'll look at. Open systems, where both matter and energy can be transferred. So a beaker. If you boil the liquid in a beaker, we can lose some gas particles as it boils. We can also see heat flowing off the beaker because it's hot. You can have a closed system. So a system where only energy can be transferred. So if I put a Tupperware container, heat it up, it's closed, and I heat it up, it'll be hot to the touch. But it didn't explode everywhere. And an isolated system. We're never going to get a true isolated system, but we can deal with hypotheticals. So a system where neither matter nor energy can transfer. And in these systems, we're going to have four types of walls. And we're just four different basic definitions. So if we could have a rigid wall versus a movable wall. A rigid wall essentially is not going to move. It's going to be stuck. But a movable wall could be a piston that's going to, as a gas pushes out, it's going to expand out. Could be a balloon surface or a bubble surface that's going to expand as the internal pressure is greater. So movable walls are going to react to changes in pressure, while rigid walls will not. And we can also have membranes, a permeable versus non-permeable. So permeable walls can allow liquids or gases to pass through. Non-permeable walls will not. So we could have permeable and rigid, permeable and movable, rigid, non-permeable, and movable, non-permeable walls. We're going to assume they're rigid and non-permeable unless stated otherwise. So when we look at the transfer of energy and matter across a boundary between system and surroundings, this is the central concept we need to worry about for equilibrium. Equilibrium, if you've had general chemistry, and if you haven't, what are you doing here? This is physical chemistry. You need general chemistry first. Equilibrium is the dynamic situation where matter and energy, both within the situation of within this reaction, and between the situation and the surroundings, the system and the surroundings, both within the system and between the system and surroundings, approach a balanced state of stability. So we're going to see essentially no new transfer of matter, no new transfer of energy. So the placid surface of the lake appears not to be moving. Equilibrium remains calm until, say, you drop a stone in that. Thus create these ripples, and equilibrium shifts until it calms down again. So equilibrium happens a lot of different ways, but a lot of times we're going to talk about thermodynamic equilibrium. So pressure, temperature, and concentration are going to change until equilibrium is reestablished and we don't see any transfer of matter and energy. So example, if I have a movable non-permeable wall within this box at a higher pressure than the surrounding situations, this gas will expand until the pressures are the same. So the pressures and temperatures are the same. The gas cannot cross this boundary, but the pressure it exerts can cause an increase in this volume until the pressure and temperature are reestablished. So which leads us to the Zeroth Law of Thermodynamics, which if you've had general chemistry, you've learned the first law of thermodynamics, which was that energy can neither be created nor destroyed. Well, the Zeroth Law is that much more important. We discovered later, but it comes almost first, which is why we label it the zeroth. So there's two more walls we need to worry about. Adiabatic, and adiabatic is a term we will come up with a lot. A wall that prevents the transference of energy from the system. It's an adiabatic solution. It's an insulated solution that essentially prevents heat from flowing out. So that helps us with that essentially isolated system. And a diathermal wall allows only the transference of heat from the system. So if we look at two examples of gases at the same concentration, if I put them, if they have different pressures for the same molarity, if I put them together in a adiabatic walls, the pressures will not equalize because heat is not allowed to transfer. Put them together, heat is not allowed to transfer, and so they just stay separate, nothing changes. But on the right side, case 2, the pressure of one goes up and the pressure of the other goes down as the temperature flows from the hot to the cold, allowing equilibrium to be established. Well, the zeroth law of thermodynamics is kind of like a commutative property. Remember, if I said A plus B equals C, well, A plus C plus B, well, sorry, say A plus B plus C is some number. Well, A plus C plus B is going to be that same number because we can switch them around. If zeroth law says, essentially, if two systems separately are in thermal equilibrium with a third, the third must be in equilibrium with each other. So if A is in equilibrium with C and B is in equilibrium with C, then A must be in equilibrium with B. And we can do that without ever having to move them close to each other and check. So why does this matter? Well, C is going to be our thermometer. So if I put a thermometer in system A and it says 50 degrees and a thermometer in system B and it also says 50 degrees, guess what? They're both in equilibrium. I don't have to touch them together to find out they're in equilibrium. So we're going to get to ideal gases and equilibrium equations of state. So one of the last two major concepts here in this first chapter is that the majority of our physical chemistry will use the state function variables, pressure, volume, and temperature. Remembering that temp and things that are be a function of P, V, and T. Now, for a gas, by plotting the variance of P with V at various temperatures, it's possible to plot a set of non-intersecting hyperbolas, like here, from 200 degrees to 700 degrees Kelvin, or PV equals A times a constant A times T. A is going to be our NR, the moles of gas times the ideal gas constant. Alternatively, we can look as A as the atoms of gas and the Boltzmann's constant. But we notice that N only refers to the total number of moles rather than the moles of individual components, because this ideal gas makes two key things. That says each gas is identical. We assume each gas to be indistinguishable regardless of what they are. That the gas has no set volume and a gas has no intermolecular interactions. Now, because of this, we can, because this indistinguishability between these gases, we can separate each gas into its own components within this equation. So, once again, we have another proof. This one's a lot easier, a lot quicker. So, okay. So, because these gases are indistinguishable, we can break apart the pressures of each gas within this situation and either look at it as one whole mixture or a whole bunch of individual gases mixed at thermal equilibrium, because they all will have the same volume if they're in the same box, and they'll all have the same temperature. So we can look at them each in individual partial pressures. So, and from there we can actually get into what's called the mole fraction of a gas. So, as we define the pressure volume P equals nRT, if we have more than one gas, we can look at this as the sum of each individual gas times their gas constant and temperature. So we're adding all the moles of gases together, divided by R and T. And that will give us the net pressure for that volume. Now, because the volume doesn't change, we can get that to the other side. So we still have the sum of each mole of gas times RT over V. Now, because this is equal to the sum of these and equal to the pressure, we can say that the total pressure is equal to the sum of each individual gas all added up. So we can, so the partial pressure is essentially the pressure of each individual gas, such that if we add them all up, dot, 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 you will get the total pressure. So the concept of partial pressure is the pressure of each gas within a system. If there's one gas, then you only have the partial pressure is equal to the total pressure. From there, mole fraction, one way we measure it is looking at the pressure of an individual gas over the total pressure. Well, the pressure of an individual gas is equal to the moles times of that individual gas over RT over V. And the total pressure, as we just said, was the sum of all the individual moles RT over V. You'll notice RT over V are the same. So those all cancel out. And so we have the moles of an individual gas over the total moles. And that will give us our term, the mole fraction, chi. This will get used a lot more later on. Chi as the ratio of the pressure of a gas versus total pressure, or the ratio of essentially the moles of a gas over the total moles. So hypothetically, do a real problem once. I filled up my tire with air the hottest day of the year, so 32 degrees. Pretty hot for with 32 psi. Preparation for my road trip the next day. Night, it chills down to 10 degrees, so you'd expect the pressure to drop. I checked my the car in the morning. I found the pressure has dropped to 27.4. Now the question here is that within spec, what we'd expect for the drop in temperature, or am I actually losing more pressure than intended? So in order to do this, we have to do some conversions. But essentially, we're going to say that, I'm going to annotate the screen. P1 over T1, because if the moles of gas hasn't changed and the volume of the tire hasn't changed, those can cancel out, equals P2 over T2. Now, one might say, oh, I need to know how many psi are in an atmosphere, how many psi are in a bar. But really, you don't, because of one little thing. if you rearrange this equation, you can say P1 over P2 is equal to T1 over T2. And so you get 32 psi over 27.4 psi. And psi over psi cancel themselves out. So the first ratio of 32 over 27.4 is 1.16. So if this is within spec, then this ratio of temperature to temperature should be 1.16. Now, one thing to note, we cannot simply use Celsius. The original equation called for Kelvin for this to work, so this needs to be in Kelvin. 32 degrees Celsius, turn to Kelvin, which is makes this 305. 10 degrees Celsius, turn to Kelvin, and it's at 283. This is still 1.167. Well, survey says no. We have 1.07. So we have lost some pressure in the gas. The temperatures cannot change, but the pressures can. So for this to be in thermal equilibrium. So what find out is, yes, we are losing air. So got to fix that. Expected volume, expected pressure should be 29.7 psi, not 27.4. Now here's an example that uses partial pressures alike. Three gases are in interconnected containers. We have a little wall barrier between the three containers. Move my own face over here just so we can see. One container, 3 bars at 2 liters. One container, 7.3 bars at 2.5 liters. One container, 5 bars, 2 liters. All three gases are allowed to mix freely. What is the mole fraction of each gas within that resulting pressure? And the resulting partial pressure. So we don't need a temperature. Well, we're given a temperature, 298. So first thing I would probably do is use PV equals nRT to find the moles of each gas. That's going to make my life a little bit easier. So PV equals nRT. So 3 times 2 over, we'll say, since it's bar liters, 0.08314 times 298. So let's record the moles of each guy. 0.0. Times 3 times 2. This first guy, 0.242. Second guy, same equation, different pressures and volumes. Higher pressure, but bigger volume. 178. Let's see. Oh, shoot. No, crap. Screwed that one up. 1.3 times 2.5. Screwed up. Okay, sorry. Yeah. How did I notice that? Greater pressure, greater volume. survey says that should be a greater amount of moles. You know, the pressure is almost doubled, but the volume is changed by only a fraction. Well, I knew that was wrong. 7366. Last one. This one should be probably the highest. So pressure of 5 bars. Yeah, we'll see. Oh God, what did I do wrong? Okay. Let's say 5 times 2. Okay. Now, okay, so 4036. So they're the moles of each one. Now here's the beauty. So the mole fraction is the sum of all these guys. So individual gas. So the mole fraction of, we'll call that chi1. It's going to be chi2, and chi3. Chi1 is going to be 0.242 divided by the sum of 0.242 plus 0.7366 plus 0.4036. Chi1 is 0.175. Well, the second one, chi2, is going to be 0.7366 divided by the sum of all those, 0.5329. And chi3 is going to be 4036 divided by the sum of all those. If you add chi1, chi2, and chi3 together, we should get 1. Sum of all assuming I did this right, or at least come up really close to 1. Okay. Yeah, that comes up really close to 0. Really close to 1. So rounding error. So the chi. Now, you get the partial pressure of each gas. If I can find the pressure of this total situation, I can find the partial pressure of each one. So now please note, the pressure of each one will change drastically because we're allowing the volume to expand to fit the total situation. Our new volume is now 6.5. If we say all gases are the same, the temperature stays the same. The total moles of gas, which we determined for our mole fractions, is 1.3822. So our total pressure would be our 1.3822 times R, 0.08314, times T, 298, divided by 6.5. So our total pressure, P, is 5.268. So to get our partial pressures, we are going to multiply 5.268 by our mole fractions. So 5.268 times 175. The pressure of hydrogen has dropped down to 0.922. Point 268 times 0.5329. The pressure of N2 has dropped down to 2.808. And the pressure of oxygen has dropped down to 1.538. Add these numbers together, they should give you back to your original pressure. So that's a very labor-intensive problem, but hopefully it is not outside the scope of our mathematical abilities. There is no calculus needed in this problem, so don't let this scare you away. A little bit of elbow grease will get us through this. Now, of course, unfortunately, gases do not act as an ideal gas. They will have a real volume. It's really small, but they will contain attractive and repulsive forces. These two effects will decrease the volume component and the pressure component relatively of our system. Because as you move gases together, if they're infinitely far away, it's essentially constant. But what we see is as we move closer, see an attractive force increasing as we get close. Then suddenly we get too close, we see a repulsive force. And so what we see, the energy of interaction drops down to be a more favorable interaction and finally shoots up into the less favorable interaction if we get too close. Now, because each gas is a little bit different, we'll see a variability based on constants A and B in what we call the van der Waals equation of state. So we see now that pressure equals nRT over V minus NB minus N squared A over V squared. As that A and B are specific to each gas, and A and B can be found in a relevant table, but they will allow for a more accurate representation of a gas. But even this van der Waals equation of state isn't perfect. And as we'll see in later chapters, much more complicated equations will exist. But this last problem we're going to run through, we'll finish out this chapter. So 1 mole of tetrachloromethane, I'm going to give you A is 20.01 decimeters to the 6th bar per mole squared, or a decimeter cubed is equal to a liter, so liter squared bar per mole squared, and B is 0.1281 decimeters cubed per mole, which is liters per mole. If it's stored in a 1 liter container at 298. So first calculate what is the ideal pressure, and then what is the van der Waals pressure according to this. So P equals nRT becomes, to keep this on stable ground, we say this is, let's erase that, move that to the other side. So we're going to say 1 mole, makes it easy. R is never going to change. 298. This whole top part is going to be the same in both equations, divided by 1. So the pressure of this situation is pretty standard, 24.7. 24.7 bars. Now, but tetrachloromethane is highly different. So pressure equals nRT B minus NB. Since N is 1, I'm going to just leave it as B. 1281 A 20.01. Since it's N squared over V squared. Okay. So 0.08314 times 298 divided by 1 minus 0.1281. So that term by itself sees a drop. So if that was alone, that would be jumped up to 28.4. But since we have this additional term, interactive, attractive term of 20.01, 20.01 drops the pressure down to 8.405. That's a huge change. And that causes us to act totally different than what you would expect. So that's where we're going to stop. That is the end of chapter 1. It's just dipping our toes in. From there, we'll get into thermodynamics. So, see you next time.